At modern training scales, AI datasets are created collaboratively by multiple data engineers rather than a single user. In a typical workflow, data engineers independently check out branches from a main dataset, perform data annotation and exploration, and commit their changes. Some branches can be merged with fast-forward merge, while others require free main merges, with conflict detection as the main branches involves. The merged dataset is then exported for downstream model fine-tuning. However, existing systems such as Parquet, Lens, Deep Lake, and Iceberg do not unify these workflows or support collaborative free-main merges. And to address this, we propose MULLER, a multimodal data lake format for collaborative AI data workflows. Here is our GitHub repository. MULLER offers 3 different interfaces to work with your data: an interactive web GUI, agent skills, and Python APIs. So in this demo, we will go through the basic idea via the interactive web GUI, which is the most straightforward and easy to follow and understand. So here is our web GUI. Now I'm logging the system as public, which is the default share user for this demo. First, I'm going to create a dataset that everyone will collaborate on. I set the dataset path, and then I load the schema from the JSON file. This step is important because I want the full Cocoa style structure, not just a simplified placeholder schema. That means the dataset will correctly include image, bounding box, category labels, descriptions, and the other fields we needed. Now I click Create Dataset. At this point, the dataset exists, but it's still empty. So the next step is to import the base CSV with 3000 samples. And in this step, I select the file and keep the detect import setting, add a commit message, and start the import. This gives us the share start point on branch main. Now that the import is done, I'll quickly inspect the dataset. The UI automatically recognizes the Cocoa style schema, so I can browse the image grid directly, inspect an image, and also see the bounding box overlay. So let me click sample 15 here. The image shows an elephant, but the current label says dog. So the base dataset already contains a labeling mistake. I'm highlighting this now because later on different users will try to fix these same samples on their own branches, and that will give us a meaningful merge conflict to resolve. So even at this stage, we are not just viewing the data, we are already spotting an annotation problem that will matter in the collaboration workflow. Next, I'll show how we can query the dataset. First, I can run simple numerical queries like an exact match on image ID. And we can see that this works immediately and are good for fast filtering. And I can also run a text query on the description field. For example, I'm searching for a description that contains the word cat. The first time I do this, the system may build an inverted index for the text field. After that, similar text queries become much faster. And you can see all the image with cats here. And after I check the results, I'll save the results as a view. Now I'll run another text query. So this query contains the word dogs. And you can see that each image here contains both a dog and a cat. Because I joined this query with the previous query with the operation end. And I'll also save that result as a view. And then I go to the Save View sections, and you can see that there are 2 views here. Both are just saved by myself just now. And you can select the view with the ID cat and reload view. And this shows the query results, which contains all the image with cats that has been materialized as reusable views instead of being recomputed manually every time. So now I'm switching from public to user A. And now I load the same dataset path again, so user A is looking at the same shared dataset, but from A's own identity and permission context. And next, user A is going to create a personal working branch. So this is important because A should not modify the main directory. The main branch belongs to public, so the write access is restricted. And I go to version control and create a new branch, dev A, and switch onto it. Now we can see that A has an isolated workspace, same dataset history, but a separate branch for independent edits. Now I'm working as user A on branch dev A, so any changes I make here stay isolated from main. First, I also plan to apply another CSV with 1000 new samples. This expands A's branches, but only A's branches. So after the import, you can see the number of samples become 4000. And next, I'll make two single sample edits. The first one is a delete. So I'm trying to delete the sample 100. The second one is an update on sample 50. So sample 50 is the one we looked at earlier. The image shows an elephant, but the original label was a dog. However, user A is trying to correct the annotation, but A here actually make the wrong guess. I update category ID to 1, which means person. Here, user A is trying to correct the annotation, but A makes the wrong guess. So now A has done 3 things on dev A: append new data, delete 1 sample, and update sample 50 with a new label. However, A may also make a mistake, so you can see the new label added by A is actually incorrect. It labeled the elephant as a person. And now I switch back to user public and reload the dataset to the main branches. What I want to show here is branch isolation. Even though A already makes several changes, the main branch still shows the original 3000 samples. I don't see A's new rows here, and I don't see A's deletions or A's label update here either. So here, the elephant is still labeled as a dog. Next, I'll switch to user B. Just like before, I load the same dataset and go to version control and create another branch, this time called dev B. So now we have 3 branches in the story, and importantly, dev B is created from main, not from dev A. That means A and B are now working independently from the same base, which sets up the merge scenario later. Now I'm switching to user B, working on branch dev B. Just like A, user B first append another 1000 samples. So B is also extending the dataset, but independently on a separate branch. Now the number of samples also become 4000. And then I make 2 more edits. First, I also delete the sample 100 again. This is the same sample that A deleted. And next, I'll go to sample 50. This is the mislabeled example we pointed out earlier. Again, the image is an elephant, and this time user B gives the correct fix. I update the category ID to 22, which is indeed the elephant. So compare with A, both users touch the same problematic sample, but they make different choices. A changes to person, while let's see B. Okay, B makes the correct guess, so B label it as an elephant. That gives us exactly kind of branches divergence we want for the final merge demo, because now the system has to resolve not just add rows, but also conflicting edits to the same sample. And now I go back to the user public again and return to the branch main. At this point, both A and B has made substantial edits on their own branches, but main is still unchanged and still shows 3000 samples. This is another important checkpoint. It confirms that the branch-based collaboration is working as expected. People can experiment, annotate, and modify data independently without affecting the shared mainland until a merge happens. Next, I'll try to merge def A back to main as user public. I open the merge panel, choose def A as the source branch, and detect conflict. In this case, there's no conflicts because main has not moved since A branched out. And before I click merge, I see the delete resolution carefully so that A's deletion is preserved. Okay, now I complete the merge. At this point, the change from def A becomes part of main. So main now includes A's appended rows, A's deletions, and A's update labels. So this is the clear merge case. Isolated work, then straightforward integration. And finally, I'm trying to merge def B into main. So now the situation is different because main already contains the change from A, and B makes overlapping edits on a separate branch. So when I detect conflicts, the system reports 3 conflict types. First, there are append conflicts because both branches add new rows. And second, there are delete conflicts because both branches delete the same sample. And third, there is an update conflict because both branches change the same label at the sample 50, but they change it to different value. And now I choose the merge strategy. For append, I choose both because I want to keep the new rows from both A and B. And for delete, I choose theirs, so B's delete is accepted. And for update, I also choose theirs, so B's correction wins. That means the final label becomes 22 or elephant, which is the correct fix. Now I click merge. So at the end, main contains the combined results, so both set of appended data, the resolve delete, and the resolve update. So you can see in the main branch, the sample already has the correct label. And if you want to go back to check the full collaboration history, so it is visible in the version graph. And the final step shows the main idea of the demo. Multiple users can work independently on branches and then merge their changes back with explicit conflict resolution. So note that the user public A, B can both be human engineer or data agents that conducts the data labeling task. And MULLER also provides agent skills for natural language dataset operations. Users can describe the operation in natural language and let coding agents finish the task. So let me show a quick example. And in this report, I've already defined custom skills under this directory. That means I don't have to tell the agent every low-level step. I can just give it a task in plain English. So here I'll say, create an image classification dataset at the directory My Photos with JPEG compressions. From that one instruction, the agent recognizes the right skills, translate my request into the report's dataset workflow, and use the existing MULLER tools to carry it out. So you can see the MULLER dataset in the right directory is created. This is what makes this skills useful. And here I'm opening a Jupyter notebook just to show that MULLER can also be used in a more hands-on way. If we want to find the control, we can also write the dataset logic ourselves by Python APIs. So in short, MULLER gives us 3 ways to work, and we can use the web GUI for an interactive visual experience, agent skills for natural language task execution, and the Python API for full hands-on control. Finally, thank you very much for your interest in MULLER and watching this demo video.